Welcome to The Explainer. Today, we're going to pop the hood on the human body and look at it strictly through the lens of an engineer. We're setting the stage for a highly mechanical, first principles breakdown of an incredibly complex yet fascinating topic: disorders of sexual development and erectile dysfunction. We're going to map out the exact neurovascular and hormonal pathways that drive sexual function in adults, and then we're going to reverse engineer how those very same pathways are first constructed in the womb. So think about it for a second. What precise neurovascular machine actually controls sexual function in real time? And perhaps even more fascinating, what happens when the original factory blueprints for that exact machine have a typo during fetal development? We are going on a reverse engineering journey today. We'll start with the adult machine in action, break down exactly how it can malfunction, and finally travel back in time to decode the embryonic instructions that built the whole thing.
Okay, let's dive right into this. Section 1, the science of an erection.
Let's walk through this exact sequence like a machine diagram. It all starts with the parasympathetic nervous system, specifically down at the S2 to S4 nerves. When stimulated, these nerves and their surrounding cells release a truly crucial molecule, nitric oxide. You can think of nitric oxide as the ultimate vascular switch. It sparks a massive spike in a chemical called cGMP. And what the cGMP does is it forces the smooth muscles to relax, which allows arterial blood to just flood right in. As the tissue expands, it physically compresses the exit veins. This creates a biological valve that traps the blood, giving us an erection, at least until sympathetic nerves step in later to reverse the entire process. Now, you might be wondering about hormones. The crucial point here is that this entire event relies heavily on one key player: testosterone. While we popularly associate testosterone mostly just with libido, its physical structural role is arguably way more vital. Testosterone literally maintains the activity of nitric oxide synthase. That's the enzymatic machinery required to generate that initial burst of nitric oxide. Without it, the engine simply cannot spark. Which brings us to Section 2, breaking the switch, looking at the pathophysiology of ED. When you compare a healthy vascular environment to a diabetic one, the contrast is honestly stark. Healthy tissue allows for robust nitric oxide release and keeps vessels nice and flexible. But diabetes, it causes severe microvascular damage. It physically destroys those delicate endothelial cells, which completely breaks the pathway. The signal gets sent from the brain, sure, but the physical vascular switch is essentially jammed. Furthermore, there are specific, everyday factors that act literally like rust on our vascular switch. Hypertension creates arterial stiffness over time. Smoking introduces nicotine-induced vasoconstriction plus oxidative stress that actively kills off endothelial cells. And, importantly, systemic cardiovascular disease causes atherosclerosis, reducing that vital arterial inflow. This is exactly why erectile dysfunction is often one of the earliest, most critical clinical markers that systemic vascular disease is silently occurring in the background. So, how do we solve this? Section 3, the PDE5 mechanical fix. Normally, your body produces an enzyme called phosphodiesterase type 5, or PDE5 for short. Its whole job is to degrade cGMP, which is the mechanism that naturally terminates the erection. Well, drugs like sildenafil and tadalafil serve as a brilliant mechanical fix for a broken system. They are PDE5 inhibitors. By blocking the enzyme that breaks down cGMP, these medications amplify whatever nitric oxide signal is still managing to get through. They basically force that biological valve to stay open longer. Now let's look at the factory blueprints. Section 4, embryonic programming and sex development. This early developmental phase happens on a rapid and incredibly critical timeline. Between just 4 to 6 weeks of gestation, the initial urogenital ridges form. Right around the 6th week, if a Y chromosome is present in the mix, a massive genetic switch gets flipped. The SRY gene kicks in and initiates the male developmental pathways. And by the 32nd week of gestation, complex processes like testicular descent are finally wrapping up, mediated by hormones like insulin-like factor 3. Now, what is really fascinating here is our starting point. Up until about 6 weeks, every single embryo is entirely undifferentiated. We all start with the exact same dual hardware, the mesonephric, also known as the Wolffian ducts, and the Mullerian ducts. It is quite literally a completely blank slate, just waiting for a genetic command. When we compare these developmental pathways, we see the absolute power of that genetic code in action. In typical male development, the SRY gene induces the expression of SOX9, which then activates and maintains male gonadal differentiation. Now, without that SRY gene, typical female development naturally occurs, driven instead by ovarian transcription factors like FOX2 and WNT4. The presence or absence of this single genetic switch dictates the entire physical architecture from that moment forward. Once those testes actually differentiate, they unleash a highly specific, perfectly timed chemical bath. First, Sertoli cells release anti-Müllerian hormone, or AMH, which forces the female ducts to naturally regress. Meanwhile, fetal Leydig cells start secreting testosterone. Crucially, out in the peripheral tissues, that testosterone gets converted into a much more potent androgen called DHT by an enzyme called 5-alpha reductase. It's actually the DHT that promotes the physical fusion of the urethral folds to fully form the penis and urethra. Which leads us straight into Section 5, Disorders of Sexual Development, or what happened when there are typos in those early blueprints. There are two primary ways this early blueprint can malfunction. On one side, we have XY DSDs. Here, the male genetic code is absolutely present, but there are defects in testosterone production or maybe a lack of that 5-alpha reductase enzyme needed to convert it to DHT. Without that strong DHT signal, the male external hardware fails to fully develop, which leads to ambiguous genitalia. On the flip side, we have conditions like congenital adrenal hyperplasia, or CAH. This often impacts XX females, where a metabolic error floods the developing hardware with an excess of androgens, causing severe virilization of what would otherwise be typical female hardware. And, these intricate variations in the early genetic blueprints are actually more common than a lot of people realize. They range anywhere from 1 in 1,000 to 1 in 4,500 live births, with congenital adrenal hyperplasia being the most common of the group. Understanding these mechanics isn't just an abstract engineering exercise for us. It is absolutely vital for how we medically approach, support, and treat these unique human developmental variations with the exact care they require. So, what does this all mean for the future? We've seen how our adult sexual function is intimately tied to lifelong vascular health, completely relying on a highly complex system that was meticulously programmed in just the first few weeks of life. As medical science pushes forward, if we can mechanically fix the adult system with PDE5 inhibitors today, how might future genetic therapies allow us to correct the blueprints before the system ever even has a chance to break down? It's a profound engineering challenge for sure, and one that really highlights the incredible, delicate complexity of the human machine. Thank you so much for joining me for this explainer.